Dynamic graphs can model data from a large variety of domains, such as protein-protein interaction, online social interaction, and e-commerce. Machine learning model can be used to model this temporally evolving structure to predict the structure of links in the future. An adversary in the real world has an incentive to add malicious edges in this input to turn the model's recommendations in their own favor or profit. Thus, studying the robustness of these models is an important problem. Let us consider this example. We are given the graph sequence on the left. The model predicts the graph on the right in the future time. Now, if an adversary were to add these edges in the second timestamp, the prediction by the model flips. However, such an attack is detectable as it changes the graph and the corresponding embeddings abruptly at the second time. Instead, an attack like the one shown below would also flip the model's prediction, but one can argue that this is undetectable as it changes the graph while following evolution at each timestamp and does not change the embeddings drastically. The central question of our work is thus, how can one formulate adversarial attacks on these dynamic graphs that can preserve evolution? In this framework, we propose that the adversary should first calculate the number of changes at each timestamp relative to the previous timestamp. Let's call it delta AT. Then he should add the perturbations at that timestamp that are no more than a small fraction epsilon times the change. Thus, he will do that for all the timestamps that are involved, and this constitutes our temporal dynamics aware perturbation constraint. Now, to find attacks that follow this constraint, we propose an effective method called TDPGD, where we first take a gradient step to maximize the adversarial loss, followed by a projection to the constraint state. We show theoretically that these perturbations would follow the requirements that we set for undetectable attack by preserving the structural and the embedding changes in the graph. Results show that PGD-based attacks can give a significant drop in the performance of the state-of-the-art models while preserving evolution. We also show that attacks can evade detection by popular anomaly detectors, in particular NICWalk, in various settings. Thank you, and see you at the conference for more detailed and discussions. Thank you.